simplest of the linear models is the mean. The equation for that model is here. Random variable y, it follows a normal distribution, and the parameters are the mean and the standard deviation. The mean, we call it gamma, the standard deviation we call sigma, and we say that gamma equals beta 0. Now this is a bit of a redundancy. Why don't we put beta 0 instead of gamma, and we avoid using an extra parameter? Yes, we can actually do that in this simple model, but in a more complex model, gamma will be a complex equation, and in this case we are going to maintain in those more complex models, we're going to maintain the gamma over there, and we give a different meaning to gamma instead of putting all these complex model in the parentheses. Okay, so graphically, the way of representing that model is like here, and we can see that in the y-axis, or in the y-axis, we've got possible values between 0 and 100. So these are possible values that the random variable y can take, and the values that can take depend on a distribution, and the distribution of values, I would like to call this a population of values. Distributions are not actual values, but I like to think them as having millions and millions and millions of values that follow a distribution. And I will come back to this later, why I make this illustration of what a distribution is, which is not very accurate, but is a way that helps me understand and will help you understand as well. Okay, so this normal distribution, the mean of that distribution is gamma or beta 0, and the standard deviation is represented here by the variability of the distribution. So the wider is this segment, then the larger the value of sigma. Okay, so two clarifications. Typically we see distributions the other way around. We don't see them turn to the right. We see the distribution this way. But the reason why I'm doing this is because when we add another variable to the model, we are going to have that variable here, and we have the y variable over there. So instead of confusing people and do first the y here and then having to transpose the y to the other axis, directly I put the y in that axis, and then when we add the x, it won't be confusing. Now the confusing part comes next. So how do we fit the model to the data? Because remember I said that the gamma or the beta 0, we need to estimate it from the data, and the sigma too, we estimate from the data. Now there are other possibilities. We may decide the distribution, the parameters of the distribution, we may decide before observing the data what are those values. And that is actually, to me, a better way of doing this. So, but it's not the traditional way. That's the Bayesian way. the traditional way is that we are going to determine those values based on the data. Okay, I'm going to show you this, and I'm going to indicate that I'm very uncomfortable with this traditional method of estimation. Okay, let's see why. Now, these y dots represent data points. So these are, let's say, human participants that are measured in variable y, and these are their values. Now, what our assumption is that those values come from a population of values that follow a normal distribution. And what's the mean of that distribution? Well, we are going to take the mean of this sample, which is 50, and the standard deviation of this sample, which is 10. And I'm not doing exact calculations. Is this just for the sake of illustration? So then we say that the random variable y takes values, or the probability of taking those values is determined by a normal distribution with a mean of 50 and a standard deviation of 10. Okay, why I'm not comfortable with this? Because I'm first saying the values that the variable y take depend on a distribution of values. And I say, okay, that's fine. Okay, what's the characteristic of that distribution of values? Oh, I don't know, but I'm going to use the values of the data that I collected, and I'm going to determine the values of the distribution. But then I use those values to the distribution to determine the probability of observing the data. So I don't like these two uses of the distribution. First, and the data. First, I use the data to determine the parameters of the distribution. And then I use the distribution with those parameters to determine the probability of the data. I'm uncomfortable with that, but statisticians for many, many years decided that there was no other way of doing this until the Bayesian methods, they were popularized, and this is done differently today.